Morning, guys. Good morning. I hope you're doing well. Today we'll talk about motion equations for constant acceleration. We've looked at some ways of analyzing or describing motion at this point, and the biggest one that we've looked at is just graphs. Today I want us to look or find a set of equations that can help us to calculate things like displacement, things like final velocity and initial velocity, things like acceleration, right? uh, for an object at any specific instant. The good thing with these equations that we're going to look at today is that you can know the exact quantity that you're interested in about the motion of the object at a specific time. You can find velocity if you don't have acceleration. You can find time. You can find displacement, depending on what you have or what you know about this object. And if you know two things or three things about the object, it can help you figure out the other three things about the object. So let's get started. We'll start off with some notation. Some of the notation we're going to be using. A is acceleration, and I don't know if I've told you yet, but for the whole of this course, acceleration is constant. We will not deal with any changing acceleration. Acceleration is going to be constant the whole time. So A stands for acceleration, and it's constant acceleration. It doesn't change. V will stand for velocity. X will stand for displacement, and T will stand for time. So before we even continue, I think I should tell you that I would be happy if you can take notes of all of the things that we're going to go through today. Taking notes will help you understand it better and will also help you have a reference for when you need to study this material again. So pull out your notebook, and as I go through these things, you take notes. So a change in time will always be considered as t because time changes from 0 to some value. So we just ignore the 0 because it would have been t1 minus t0, but t0 is always 0 because it's the starting time. So we'll just use t1, which we just are comfortable calling t. A change in displacement, I think you remember this, will be given by x1 minus x0. And as you can see, this textbook does not use x1 because x is just considered final position. But for consistency, and it's because it's used a lot in the epiphysics notation, we are going to use x1 and x0. The change in velocity, the same thing, will be v1 minus v0. These are vector quantities, so yeah, they have the bars on top. Acceleration is constant, so we'll just represent it with a. So let's start with displacement. Solving for displacement and final position if we know the average velocity, and always remember the acceleration is constant. So starting with displacement, I'm going to take you back to the definition of velocity. We know that velocity is the rate of change of displacement, right? So a final velocity is the rate of change of displacement. How fast an object changed its position is final velocity. So if I break this down, this will be, I know change in displacement is x1 minus x0. So that will be x1 minus x0 divided by t. By the way, if you hear a basketball bouncing in the distance and it's bothering you, you can thank Salat for that. So if I cross multiply here, or if I multiply both sides by t, then I'll have final velocity times t is equal to x1 minus x0. And if I take the x0 to the other side, if I add x0 to both sides, then I'll have x0 plus vt is equal to x1. So this is our very first equation of motion. If I want to find the final position of an object, I'll just take its initial position, and then I'll add its final velocity times how long it was moving for. That's our very first equation of motion. And just to note, this velocity that we're using here is the object's not final velocity, average velocity. This is the object's average velocity. So if I want to know what the object's average velocity is, that one is simply, average velocity is simply the initial velocity plus final velocity divided by 2. That is simply what average velocity is. This is also another important equation. This is the average velocity of an object. So we can call that our second equation of motion, average velocity. All right, moving on. So what if I want to find the final velocity from the definition of acceleration? Or what if I just want to find the final velocity of the object? Well, I know that the definition of acceleration is that acceleration is the change in velocity, right? The rate of change of velocity or change in velocity over a given time. So my acceleration will be v1 minus v0 because that's the change in velocity divided by t. And if I cross multiply here, I'll have a times t is equal to v1 minus v0. And if I add the v0 to both sides, then I'll have v1 is equal to v0 plus acceleration times time. This is our special third equation of motion. Third equation of motion. v1 is equal to v0 plus acceleration times time. So if I told you that, for example, if Solomon started out, or you were looking at Solomon and you started seeing him when he was running at 3 meters per second, and then he accelerated he ran with an acceleration of 1.5 meters per second squared, and then the question is, what is his final velocity after 3 seconds, right? Well, you would just use the equation. You just say final velocity is equal to initial velocity plus acceleration times time. You say final velocity, initial velocity is 3, acceleration is 1.5, and time is 3 seconds. So then that would be 3 plus 4.5. So his final velocity after 3 seconds is 7.5 meters per second. Another example can be there's a car that's moving at, say, 150 kilometers per hour, right? Then the driver is moving so fast, he sees the cow. When he sees the cow, he starts to decelerate. And his deceleration is slowing down, right? He sees the cow, he slams the brake, he starts to decelerate. And let's say he decelerates at 8 meters per second squared, right? And the question is, how long will it take him to come to a stop? We can apply this very same idea, that the final velocity v1 is equal to the initial velocity v0 plus acceleration times time, right? So we know that because he is going to a stop, his final velocity will be 0. This is his initial velocity, but his final velocity has to be 0 because he's going to stop, because he's seen the car on the road. So our final velocity has to be 0. Initial velocity is 150 kilometers per hour. I hope you guys remember how to change from kilometers per hour to meters per second, right? If you don't remember, you can look it up on YouTube or on Google, but it's basically multiplying by 1,000 and dividing by 3,600, because there's 1,000 meters in 1 kilometer, and there's 3,600 seconds in 1 hour. So if you divide that and you reduce it, it reduces to this fraction. Plus, the acceleration is 8 meters per second times the time which we're looking for. So when I solve for this, I think you'll see that you'll get a time which is a negative value, but the reasoning for that negative value, because time cannot be negative. It's impossible to have negative time, otherwise you'll be going back in time. The reason for that negative value is because this is a deceleration. This is an acceleration that is in the opposite direction of the motion, so then we should have used the negative for the acceleration there. So that solves everything, and we get our time as positive. As of course, I would like to see this answer in your books solved and completed. Okay. What if I want to solve for final position when the velocity is not constant, right? Velocity is not constant. How do I solve for final position? Because the very first thing we looked at was how I can solve for the final position, this one here, but we took the assumption that the velocity was constant. But now what if the velocity is not constant, right? How do I solve for the final position? Here, we're going to do some algebra and combine these two equations. Just combine this equation with this equation to find what we need. So this equation says that x1, or the final position, is equal to the initial position plus average velocity times time. Well, do you know what average velocity is? Sorry, I meant to say combine this equation and that equation, those two. Average velocity is, according to that equation a couple of slides ago, average velocity is v0 plus v1 divided by 2. And I'm multiplying that by t, right? So I have x0 plus, let's break this down and see what happens, v0 t over 2 plus v1 t over 2. Okay, we have final position is equal to initial position plus v0 t plus v1 t over 2. But however, the saying velocity is not constant. So velocity is changing. That means we don't know what the final velocity is, right? So we need to get rid of this final velocity term in this equation. How do we get rid of this final velocity term? Take you back here. It says final velocity is initial velocity plus acceleration times time. So that's what I'm going to substitute for. Final velocity is equal to initial velocity plus acceleration times time. That's the substitution that I'm going to make. So I'll have x0 plus v0 t divided by 2 plus, instead of v1, I'll have v0 plus at over 2 times t. Then I just need to expand this. So I'll have x0 plus v0 t over 2 plus, again, if I bring the t inside, I'll have v0 t over 2 plus a times t squared over 2. I hope we can all see that. And I'm going to use some magic here to make everything smaller. No. Use some magic. No. So give it a second. Magic always takes time to work. Magic. Yay. Yeah, so that's the magic. Now I have x0, we'll just write it in bigger terms, plus v0 t over 2 plus another v0 t over 2 plus 8t squared over 2. So when I have something, when I have two halves of the same thing, I hope you remember that that's equal to one whole thing. So here I have two halves of the same thing, right? v0 t over 2 is being added to v0 2 over 2, so that is just v0 t, x0 plus v0 t plus 1/2 at squared. That is final position. So this is, I think, one of the most useful equations of motion, and we'll call it equation 3. In some books, you'll see it written as, because you see it written as change in position equals v0 t plus 1/2 at squared. And it's the same thing, because when you take this x0 to the other side, when you take this x0 to the other side, then you have x1 minus x0 equals v0 t plus 1/2 at squared. And basically, x1 minus x0 is what we call a change in position, equals v0 t plus 1/2 at squared. So, like I said, this is one of the most important equations of motion. Oh, sorry, I think it's number 4. One of the most important equations of motion. So, if you forget all of the other ones, don't forget this one. And in any case, you'll always have a formula sheet which you can refer to use the equations. All right, let's look at our last equation of motion. If I want to solve for final velocity when velocity is not constant, again. So again, I'm going to do some algebra, starting with this equation that v1 equals v0 plus acceleration times t. Right? Now, what if I wanted to eliminate time? If I wanted to eliminate time from this equation, because what we want to look for is a timeless equation. If you notice, this equation here does not have final velocity, right? This equation here does not have displacement. There's no displacement at all. Out of the 5 quantities we started with, out of these 5 quantities, time, displacement, velocity, acceleration, out of those, 4 quantities, there's an equation that doesn't have each of them, which makes it easier for calculations or computations. So we want to find one that does not have acceleration. In order to do that, we have V1 is equal to V0 plus AT squared. But I hope you remember that from this equation here, or let me do it this way. If I square this whole equation, right? If I square the left-hand side, I have V1 squared. And if I square this side, I have V0 plus AT squared. What is it, AT squared? Oh, wow, sorry. I bet you've been screaming the whole time. It should not be V80 squared. It's just V0 plus AT. Yes, thank you. So V0 plus AT, if I square both sides, I'll have V1 squared is equal to V0 squared plus 2 V0 AT squared plus A squared T squared, right? So what I have is V1 squared equals V0 squared plus, I'm going to take out some like terms. 2 is, I'm going to take out 2 for purposes you'll see in a second. I'm also going to take out A, and I'm going to take out T, 2V0, no, I don't take out T. I'm going to take out 2 and A, right? If I take out 2A, I'll have left here V0 T. What's happening? I did my expansion wrong. When I expand this, it should not, wow. Expand this, it should not be T squared in the middle term, it should just be T. Thank you, Solomon, for catching my mistake. Okay, continue. So I'll take out 2 and I'll take out V0. No, I'll take out 2 and A. When I take out 2 and A, I'll have V0 T, right? Because I took out 2 and A, I'll have V0 T. On this side, if I take out A, I'll only be left with 1A T squared. And since I took out T, sorry, A, I mean 2, that will be a half. So what you see here is that what I have inside the parentheses is basically V0 T plus a half AT squared. And when I go back here, V0 T plus a half AT squared, that is the same thing as change in displacement. So I'll just substitute for all this here with one term, which is called change in displacement, right? So this is our fifth and last equation of motion. V1 squared is equal to V0 squared plus 2A delta x. Now, I know I messed up a lot on this one, so you might start wondering if it's this hard for this guy. What about us? Well, this was a simple step of expanding and factorizing. So just because I'm too old and can't remember my factorization doesn't mean that it should be too hard for you. Secondly, no one is ever going to ask you to prove or show how these equations come to be. The idea is that you're able to use them. You're exposed to them because you're in the AP Physics 1 class, and if any requirement ever comes, you know where these come from, but no one is going to ask you to prove them or to derive them. So that, I think, can give you some assurance or consolation. But we need to know how to use them. So that's the important key. So just summarizing them again, the very first one was x1 is equal to x0 plus v times time, and this was average velocity. That average velocity is given as v0 plus v1 over 2. Final velocity is v0 plus at. Displacement is final displacement or final position is initial position plus v0 t plus a half at squared. And the last one was v1 squared is equal to v0 squared plus 2a change in displacement. If you want, you can rewrite them for yourself, write a summary somewhere that can be something like x1 equals x0 plus vt, v average velocity, v0 plus v1 over 2 V1 is equal to V0 plus AT, and change in displacement is equal to V0 T plus a half AT squared, and finally V1 squared is equal to V0 squared plus 2 times acceleration times change in displacement. So those are the equations. Now we just need to start using them. So one thing I want to tell you before you start using the equations is just identify the information that you have. Usually out of this information are like position or distance moved, final velocity, initial velocity, acceleration, and time, right? Out of these 5 quantities, you just need 3, and then you can find the other 2. Usually you are given 3 of them, then you can use the 3 you're given to find the other 2. So write your list at the beginning like this, and then identify what you have. Then you can use what you have to find what you don't have. So on a dry concrete, the car can decelerate. So from the very beginning, we've been given an acceleration of negative 7.0 meters per second squared. Whereas on a wet concrete, this is on dry concrete, right? On wet concrete, it can decelerate at a rate of only 5 meters per second squared because it's more slippery. Find the necessary distance to stop a car. Stop a car, that's giving you a hint. Because it's stopping, the final velocity is going to be 0 meters per second in both cases, on both the dry thingy and on the wet thingy. The final velocity will be 0 meters per second. For a car moving at 30 meters per second, so this is giving you its initial velocity, 30 meters per second. It's the same initial velocity, which is 30 meters per second on both dry and wet concrete. So they're asking us for distance on both dry and wet, and yeah, that's all they're asking for. If they wanted, they could also have asked us for the time for both dry and wet, but this question didn't ask for it. So all you need to do now, because I already have 3 out of the 5 quantities, I can use any of these, these 3 to find the displacement that's being asked for. So I need to find an equation that has displacement, that has velocity, initial velocity actually, and that has acceleration. Yeah, so that's the equation I'm looking for. An equation that has displacement, final velocity, initial velocity, and acceleration. And when I go and look at my list of equations, the equation that has all of those quantities, displacement, check, acceleration, check, initial velocity, final velocity, check. So I'm going to be using that equation, that V1 squared is equal to V0 squared plus 2 times A times change in displacement. So I'll start solving for the dry concrete, which is red. So for the dry concrete, the final velocity is 0. The initial velocity is 30 squared, 0 squared, 30 squared, plus 2 times the acceleration is deceleration, which is negative 7 times change in displacement, which I am looking for. So this is a very simple math equation because it's just 30 squared minus 14 delta x. So I can take the 14 delta x the other side, and that's equal to 30 squared. And I hope you can see that the change in displacement will be 30 squared divided by 14, which gives you the answer to that. So for the other part, for the wet surface, you do the same exact calculation, except you use a different deceleration of 5 meters per second. So yeah, I hope you can show me this on your pictures, done and completed. This is your homework. Enjoy.